Hello, Mr. Simpson here with our first video for Chapter 14, Section 1, Bronsted-Lowry Acids and Bases. The learning objectives are listed here for you, so please pause the video and copy these in your notes. Our first task in this unit is to identify the acid and base in a reaction, more specifically, the Bronsted-Lowry acid and base. So in order to do that, we first have to take a look at the definition, which you see listed here. If I look at the reactions below here, I can see what happens with regards to my hydrogen ion. So if I think about this, the term proton, what happens here is we are talking about the exchange of the hydrogen ion. So if we think about hydrogen having an atomic number of 1 and a mass number of 1, basically, hydrogen is 1 proton and 1 electron, no neutrons. So the hydrogen atom, when it forms an ion, it's going to lose that 1 electron, and it is going to then become the hydrogen ion, the H+ ion. So when the hydrogen atom with only 1 proton and 1 electron, 0 neutrons, loses the electron, it is basically what's left is just a proton. So that's where the terminology proton acceptor, donates a proton, accepts a proton, things like that. Okay, so as I look at my reaction here, I can see what happens is that initially I start with HNO3, and after the reaction that becomes NO3-. So what happens here is the HNO3 donated the NH+, a proton, to the water. And you can see the water then became H3O+. So in terms of our definition, the Bronsted-Lowry acid would be the HNO3, the thing that donated the hydrogen, and the base would be the water, the substance, the compound that accepted the hydrogen. Now take a look at this next reaction and see if you can identify the Bronsted-Lowry acid and base. Now, if you took a look at this one, you would have noticed that NH3 becomes NH4+, so it actually gained a hydrogen. So in this case, the water was the thing that donated the H+. And so the water is our acid, and NH3 that accepted the H+ is our base. Okay, as we now know, reactions are reversible. So you see here our reactions can go both ways. So if I think about this reaction going from right to left, I can also identify an acid and a base. So if I go back to our first one and take a look here, H3O+ becomes H2O. So what happens going this direction is the H+ donation happens this way. And so we would call our H3O our acid, and our NO3- our base. Actually, what we call them are the conjugate acid and conjugate base. And you can see those definitions right down there below. And so what we identify are conjugate acid-base pairs. And hopefully this makes some sense as I look at the relationships here, that the acid initially, the thing that gave up the hydrogen, becomes the conjugate base. So if in the forward direction it's donating a hydrogen, it makes sense that in the reverse direction it would be accepting a hydrogen. So something that's an acid in the reverse direction would be the conjugate, an acid in the forward direction would be a base or conjugate base in the reverse reaction. And then our base becomes our conjugate acid. Okay, if I take a look at labeling our second reaction here, you can see what's going to happen here is the H+ ion is going to go in that direction. So that means our NH4 is our conjugate acid, and our OH- is our conjugate base. I can see this by looking and see what happens as I go from right to left or left to right. And once again, those relationships should make sense. The base in the forward direction becomes the conjugate acid in the reverse direction, and the acid in the forward direction becomes the conjugate base in the reverse direction. Now, in these first two examples, you may have noticed something interesting happen. In the first example, water is acting as our base, our proton acceptor, accepting a proton. And in the second reaction, our water is acting as an acid, donating a proton. Water is amphiprotic, and you can see that term right here, amphiprotic. That means it can either accept or donate a proton. So it can either be, if you put water with an acid, it's going to accept a proton and act like the base. If you put water or put a base in water, it's going to donate the hydrogen and act like an acid. This leads us to what's known as the autoionization or self-ionization of water. Water, because it can either donate or accept an H+, and if we let's just say this goes with this species, and then this water species goes with this, okay? We can then say here that the first water accepted an H+, so that the H+ went this way, and so this is our base, this is our acid, okay? So then this would be our conjugate acid, and this would be our conjugate base, okay? Now, this is particularly important because the concentration of these two species, the hydronium ion, H3O+, and the hydroxide ion, OH-, represent our acidic and basic characteristics of solutions. Acidic and basic characteristics. So if there's more H3O+, or sometimes just shortened to H+, concentration in a solution, our solution is going to be acidic. If it has more OH- concentration, it's going to be basic. If I think about writing a K expression here, products over reactants, coefficients become exponents, exclude solids and liquids. Since on the left I have all liquids, my expression would be the concentration of those two ions. And we are going to give this a new designation. This is Kw. And Kw is the ion product constant. And it has a value of 1 times 10 to the negative 14th. So that means that for neutral water, that's not acidic nor basic, so neutral water, that would mean that our H3O+ concentration and our OH- concentration need to be equal. And that would mean they would be 1.0 times 10 to the negative 7th, both of them, for neutral water. Now, because they always multiply together to equal 1 times 10 to the negative 14th, if I have more H3O+ ion concentration, the result means I must have less OH-, right? So they're going to operate in that fashion that they both can't be greater than 1 times 10 to the negative 7th, what the neutral value is. If one becomes greater than 1 times 10 to the negative 7th, then the other one must become smaller than 1 times 10 to the negative 7th. Okay? And this allows us, this is our first example of how we can determine if a reaction is acidic, basic, or neutral. And you can see that relationship down below here. If our H3O+ is greater than 1 times 10 to the negative 7th, that must mean that our OH- is less than that value, and then my solution is acidic. Since the H3O+ is the acidic nature of a solution, if I have a greater H3O+, then my solution will be acidic. You can see the other example here. If the OH- is greater than 1 times 10 to the negative 7th, that means I'm going to have more OH- than H3O+, so my solution is going to be basic. Let's take a look here at an example problem. Go ahead and pause your video and copy these down in your notes. We'll do the first one together, and then I'll give you a chance to work the second one on your own. Okay, so as we saw a second ago, we know that Kw equals the concentration of H3O plus times the concentration of OH minus. I know my Kw is 1.0 times 10 to the negative 14th. So in this case, we know our concentration of our H3O plus is 3.98 times 10 to the negative 13th. So that just means I can divide and I get an OH minus concentration of 2.51 times 10 to the negative second, and the concentration there is molarity. Okay, I can see here that my OH minus concentration is much larger than my H3O plus concentration. And now that I have the two values to compare, I can go ahead and compare them. I actually could have answered the second part of this question, is this acidic, basic, or neutral, before I even did the calculation, right? Because since my H3O plus is larger, much smaller than my 1 times 10 to the negative 7th, that means that the OH minus had to be much larger. And so you can see that. And just to make sure we're on the same page with regards to that kind of negative power of 10 here. So this value is this, and our answer is this. So this is what I'm talking about. Remember, so the smaller that negative exponent, the larger the overall value is. Okay, so clearly this reaction is basic. I could have identified that before even doing the calculation, but I can also then do the calculation and compare those two values. Okay, why don't you go ahead and pause the video and attempt this next example problem on your own. Okay, here's the proper setup for this second example problem. Again, I would be using my Kw, 1 times 10 to the negative 14th, divided by, in this case, they gave me the OH minus concentration, so I would be getting the H3O plus concentration. Again, since the OH minus concentration they gave me in the problem is so small, smaller than 1 times 10 to the negative 7th, I would have said before even doing the problem that this is acidic. And then as you can see, if I compare those two values, the larger of the two is the H3O plus. Okay, this wraps up the video for our first unit in chapter 14. Go ahead and go on to the second video here for your first night homework.